Dante Certification Level 1, Second Edition, Basics of Digital Audio. We probably all know that sound is created with things that vibrate. That vibration pushes air molecules around it, which then hit other air molecules around them, and so on. Effectively, that creates tiny vibrations in air pressure. So when we draw a sound wave like this, you could think of the middle line as nominal air pressure, then the sound wave variations above and below it. Here is a moment of compression, and here is a moment of rarefaction. When we capture this as digital audio, we take readings of the wave's amplitude at a steady interval. So, this is what the information tells us. And if we look at the raw data, you can imagine that digital machines could connect the dots on playback and reproduce the sound wave once again. Now, when these readings are taken, what do we call them? Well, if we have a collection of them, we might call it a sample, right? There would be multiple readings in there that makes an audio clip. We would call that a sample. But if we're talking about one reading, there might be a very specific term of a digital word. And you might hear of people speak of bit depth or word length. That refers to the number of binary bits used to record this reading. Basically, using more bits means we have more resolution. We have more steps on this ladder. CDs operated at 16-bit. Most professional production is done at 24-bit, and some equipment will go up to 32-bit. Dante can manage all of that. And as you probably figured out, the horizontal axis represents time. So we increase resolution in time by taking more readings per second. CDs worked at a sample rate of 44.1, or 44,100 times per second, and most professional audio works at 48K, or 48,000 times a second. About this point in the explanation of digital audio, usually instructors will bring up Nyquist's theorem. Now, simply put, Nyquist's theorem states that your sample rate should be at least double the highest frequency you wish to capture. So, why is that? Well, let's take a look. One cycle of a wave will include a peak, an area of compression, and a trough, an area of rarefaction. That forms one cycle of a sound wave. Of course, you'll need at least two samples to capture each part of the cycle. Now, to be clear, Nyquist was not implying that high frequencies would just roll off if you didn't set your sample rate high enough. This isn't something like an old analog cassette problem. To demonstrate, here's a sound wave with 7 cycles. Now, Nyquist states that our sample rate should be at least double the frequency, right? So if we have 7 cycles, then we should have at least 14 readings. Let's see what happens if we don't do that. Let's capture this with 8 readings. Okay, so I drop my grid in there, I take the readings, and to make this perfectly clear, I'll fade the original wave to the background. Now, when the system reconstructs a wave with this data, what will it create? We get an alias of the original frequency. Okay, let's do this again. This time we'll follow the Nyquist theorem. I'll go beyond double the highest frequency, right? So if I've got 7 cycles, let's capture this with 32 readings and see what happens. Again, I drop my grid in there, I take the readings, and I'll fade the original wave to the back. Now when we reconnect these dots, we'll get right back to the original wave we started with. Now, to prevent problems with alias frequencies, your analog to digital converters will always have a low-pass filter in front of it, knocking out frequencies above 20,000 hertz. This way, your 44.1 or 48K sample rates will be just fine. Okay, so let's see where we can set our sample rate and bit depth for Dante devices using Dante Controller. In Dante Controller, we already showed you the routing grid. Well, if I double-click a device name anywhere, we'll get a new screen. What you were looking at before was Network View. Now you're looking at Device View. Network View allows us to see a small bit of information about every device at once: firmware, clocking, network status, and so on. These are great for getting an overview of all devices. But Device View shows us more information about one device at a time. At the top, I can change which device we're looking at in this drop-down menu. If I select the Device Config tab, you can see I can choose the sample rate I wish to use. This particular device offers sample rates of 44.1 and 48K, as well as high resolution rates that are doubled or quadrupled from that point. So yes, this particular device can support up to 192 kilohertz. It also allows for pull-up and pull-down sample rates. Now, if you don't know what pull-up and pull-down sample rates are, that's okay. Leave it set to none. The only time these really come into play is if we're converting film to television or television back to film. So it's used by the broadcast industry. If you're building an auditorium, a conference room, right, something like that, you're not using pull-up and pull-down rates. So leave it set to none. Now over here, we see a setting talking about preferred encoding. This refers to your bit depth or your word length. On this particular device, it's fixed at 24-bit, so it's telling us we can't change anything here. However, I can pull up a second device. Oh, and by the way, as you can see, we can have multiple device view windows going at the same time. This is great for comparing settings between devices or monitoring multiple devices at a time. On this device, we'll see it only supports the sample rates of 44.1 and 48K, as well as the pull-up and pull-down rates around that. But this device allows us to use 24-bit or 32-bit audio. So, different devices will have different options available within them. Now, when we're making a subscription between two devices, the sample rate will need to match, but the bit depth can vary. Let's take a look at why. We can visualize the linkages between equipment as a gearing mechanism. The sample rate could be visualized as the spacing of the teeth, and the bit depth could be the depth of the teeth. If we have a match, of course, the gears fit together perfectly and they work as expected. A mismatch of bit depth can be visualized as a difference in the depth of the teeth. Gears may still work together like this. If we're going from a higher to a lower bit depth, we can simply drop off the least significant digits to achieve the desired size. If we're going the other way, from a lower to a higher bit depth, we can fill in the least significant digits with zeros and be on our way. This is a very simple thing for systems to manage, and it does allow for these devices to work together. So, what happens if we have a mismatch of sample rates? Well, now we have an issue. Again, the sample rate is like the teeth of the gears, and it doesn't match up at all. So quickly, I'll show you a Dante system with multiple sample rates. Here I have two devices that are capable of 96K operation, so let me change that setting. If we look at this icon in the toolbar, it will bring up a list of things we can filter for. In our case, I want to focus on audio sample rates. When I open that, we'll see I have a list of options for the two sample rates that are currently present in our system. If I choose 48K, you'll see the two 96K devices drop off. But of course, this is more dramatic when I choose 96K, right? So if your network has multiple sample rates going on at the same time, this can be an easy way to find the devices that can connect to each other. Let's suppose you had an auditorium running at 96K, but your distributed audio system was running at 48K. This would be a very simple way to filter that. Of course, if I try to make a patch between two devices that are running at different sample rates, Dante Controller won't let me do it. Okay, so let's move over to the Clock Status tab. At the top, we'll see that my mixer has been chosen as the clock leader for all devices. Indeed, if I look down the list of devices, I will see that mixer as my clock leader, even though we have multiple sample rates going on my network. For that matter, we have video devices on this network, but we also don't have a separate clock for their frame rates, right? In a Dante system, the clock leader will distribute a time and date stamp so accurate that any device can then derive whatever sample rate or frame rate that they wish from that reference. So, there is only one clock leader regardless of how many sample rates or frame rates are present. So as we said earlier, we can't digitally connect two devices at different sample rates. But if you want to keep the connection digital, you could use a sample rate converter. Dante doesn't do this as part of our chipset, but a manufacturer could add one to their product. A sample rate converter is a device with two digital ports, one running at each speed that you wish to connect. In our gearing example, we'll represent this as two gears on a common axle. Each gear can now connect to a different port on a different sample rate. And now the audio can pass. Now, realistically, individual systems will likely be designed at a single sample rate. However, there could be multiple systems on the network, and they may need to connect. Let's suppose a facility had an auditorium operating at 96K and classrooms or conference spaces at 48K. The devices in each group would be able to see each other on the network, and they will elect one clock leader. Now let's suppose we wanted to make a connection between these two spaces running at different sample rates. Maybe we wanted to be able to get an overflow feed from the auditorium into the conference spaces, or somebody speaking in the conference spaces to the people in the auditorium. So here comes the sample rate converter. It has two Dante ports on it, one running at 48K and another running at 96K. Make your subscriptions to the port running at the proper speed, and you've made a link between them running digitally the whole way. Now, of course, it might also be an option to simply take the auditorium system and flip it to 48K so everybody matches. That would also be an option. The choice is yours. Okay, so we know we have all this data moving around the network. To understand how much bandwidth this takes, it's important that we realize we are working with more than just the raw audio data. So if we think about a delivery service, they're not interested in the size and weight of the item you're shipping. They want to know the total size and weight, including all the packing material, the box, and all of that. Well, so it goes with networking. When we're estimating bandwidth, we can't just look at the bandwidth of the audio. We also have to know all of the information we add to that to allow it to route across the network. A good practice is to limit your use to 512 channels of audio on a 1 gigabit link. If we do the math, the raw data from 512 channels of audio at 24-bit 48K would be about 590 megabit per second. But once we add the network overhead, we're transmitting about 768 megabits per second. The easy rule of thumb is to limit your use to 512 channels of audio on a 1 gigabit link. Now, another good principle to understand is that on a network, you do not want to use all of your bandwidth. When you're sending data across the network, sometimes there's small gaps in between the packets as they're sent. You could visualize it as ice inside of a glass. No matter how I stack these ice cubes, there will be small regions in between it that go unused. And in the case of a glass, that's where a drink goes, right? But a good rule of thumb is limiting yourself to about 80% of your network bandwidth, especially for a beginning networking class where we're not even going to talk about optimizing switches yet. And even with that safety margin, Dante represented a huge capacity leap over its predecessors using the same category or fiber optic cable. And of course, Dante networks can scale with network capacity. So if you were to get a 10 gigabit switch, you could have 10 times this capacity, which was not true of older systems. Now, when we're working with higher sample rates, they are typically a multiple of the 44.1 or 48K sample rates. So the bandwidth is right about double for a 96K signal. So if you wanted to know the capacity of a 1 gigabit connection at 96K, you've doubled the sample rate, you would reduce the number of channels by half. If you quadruple the sample rate, you reduce the channels by a quarter. Now, when we're speaking of the number of channels that can fit down a 1 gigabit link, we don't want to get that confused with the capacity of a 1 gigabit switch. Let me explain. In the early days, we didn't have network switches. We had network hubs. They worked by taking a signal that came in one port and repeating it to all other ports on the switch. Now, if two devices transmitted at the same time, there would be a data collision. And of course, both devices knew that happened. They would wait some random period of time before retransmitting again. And this was horribly inefficient. So thankfully, that's not the way our networks work today. Today we use network switches, which are much smarter. Switches map out the network. When they receive a packet, they look at the recipient and only send the message out the port that leads to the destination. While one device is transmitting to one port, another set of ports can have a separate conversation, totally independent, both of them going full speed. If two devices were to transmit at the same time to the same port, the switch would buffer the information and send the data in a first-come, first-served basis. Two devices can naturally send down a single path without worry, but of course that path would allow 512 channels of audio in total. So you would split this any way you like. As a great illustration of the point, take a look at this story from Solid State Logic. Before sending out equipment to a new broadcast facility, they tested it all at their headquarters. You can look through the accumulated capacity here, but this system delivered over 24,000 channels on the network, and that worked just fine. So clearly, Dante networks have incredible capacity and scale very nicely. Okay, so let's sum this up. When we capture audio digitally, we describe the amplitude of the sound wave at a regular interval. The bit depth represents the resolution of the amplitude, and the sample rate represents the resolution in time. When we make a connection between two Dante devices, they must operate at the same sample rate. However, bit depths can be mixed. On a 1 gigabit link, you can safely get about 512 channels of 48K 24-bit audio. And of course, Dante can scale. If you have a faster link, you can get more channels. And because of the way network switches work, don't confuse the capacity of a 1 gigabit link with the capacity of a 1 gigabit switch or even a 1 gigabit network. The network can maintain independent connections between devices, so you can have thousands of channels on the network. No problem.